standards say it, so you may have to do it. So what my recommendation is that when you do a test, supplement it with another test that's more cited. In the field, of course, there's absolutely no point going to the guy who is bringing the concrete in the field, who doesn't know anything about it. There's absolutely no point arguing with him. Let him do his slum test. But when you are developing mixers, you say, okay, anybody who wants a slum test, here is a 75 mm slum, 100 mm slum for my concrete. But if you want to really know why that slum is, here is a much better test, and here is how my concrete is behaving, so that it becomes replicable. You can take it from one lab to the other. Okay? So you have to be very careful about testing the why question. I want you guys to be very careful and focus on the why. So when you try to publish, and I'm an editor for 2 journals, and I handle about 1,500 papers a year. I get 1,500 papers a year that I handle from all over the world, and I immediately reject, without even sending out for review, any paper that does not answer the why question. If somebody sends a wonderful paper, I tell them, this is not the journal for it. If you have a lot of wonderful results, so if something, for example, comes from India with a lot of wonderful results, so I have used a special fly ash, it's available in this part of India, and I've used the concrete, I've got very great strength. I said, wonderful work. Please send it to a journal that's right next to your house or right next to your college, so that this technology is, people are aware of this technology in the part of the world where this material is available. In the US, in Europe, in Australia, it doesn't help if there is a small pocket of fly ash available in Andhra Pradesh. It doesn't help anybody. It doesn't help you. It doesn't help. You use it for your local so that you can make this people more aware of. And if the why question is not answered, many journals will not. I don't know if you guys have noticed. There are so many journals these days. You can pretty much publish anything. You can write your life story and send to a journal of some journal of civil engineering in some crappy thing. You can send it, they might even publish it. Wonderful life story of a civil. I always tell this example, right? So in school, when I was learning Hindi in school, right? We started Hindi in 5th grade in Kerala. We had to learn Hindi, and it was always starting with guy. First thing is study the cow, right? About the guy and all that. So one of the joke that I always say, you learned to write 5 sentences about the cow for the Hindi essay in 5th grade, but they asked about coconut tree. So I say, cow is tied to the coconut tree, and then I write 5 essays about 5 sentences about the cow. Right? So because I don't know anything about the coconut tree to write in Hindi. This is what a lot of people do. You don't explain what is happening in the system, you write about everything that Neville's book has or Emma Shetty's book has. When it's already published in a book, when it's available for everybody, the world doesn't need to know from you. The world needs to know from you what you have to give and what is your contribution. So be very careful. Otherwise, if you do that, you can avoid being disappointed with a lot of rejection letters. And it happens. Some rejection is always there. Not everybody will accept what you do, and that's totally fair. But you should do the best work possible and explain why. And many of the tools that I'm giving you in the next 5 days are pointers towards explaining the why part of the story. Because how is well known? How to make concrete is well known. Whether they do it or not is a different story. But how to make concrete is well known. How to get a high strength. So again, the other thing I tell them is, oh, I got 80 megapascal strength. Doesn't matter, I can give you as high a strength as you want. Strength is not a problem at all. Is my concrete durable? Do I know that all the mechanisms are taken care of? Do I know the chemistry well enough to explain why I'm getting it? Right? That is what you want. And that's also the reason why I said yesterday that technocrats have to be in the process of decision making. To give you an example, you have a specification for a concrete for a certain construction where only strength is specified. And somebody says, I'll give you the best strength concrete. And the technocrat sits here and picks, oh, this was asked, this is there. This was asked, this is there. But you, as somebody who knows the material, might be able to say, yes, I know why. This concrete has a lot of alumina and it has a lot of sulfates, and they're giving you a high 14-day strength because of a trigger. It's not because of what I want. Leave it for 90 days and see what happens, right? Then you might know it. But will a technocrat know that? He will say, oh, and they might say 7-day, 3-day strength, 7-day strength, 14-day strength. Because my 14-day strength is 40 megapascal, I expect a 50 megapascal 28-day strength. Very reasonable, very logical for somebody who's looking at it. But is that how it is? No. You might have some other chemical reaction going on. Right? You might have something that gives you good strength now, but the chemistry might be that it might form delayed ethylene in 5 years. You might put it in a high temperature environment. When I was working in India before I went to the US, I did a consulting thing for a company that was making brake pads for cars, right? So there were there was a furnace, high temperature furnace that the brake pad, the ceramic pads had to go through, and the furnace lining was falling off very quickly. And they put in ceramic furnace linings, and the linings were falling off very quickly. They all tested the strength, they tested the chemical properties, and finally they couldn't do it. So I was asked to go and look at it. And so we did some SEM imaging of that, and I could find not ethylene, lot of needle-like particles in there. Because I knew only about ethylene, so I did not know what those particles are. And these are basically high sintered silica ceramics. So basically what had happened was there were some impurities in the form of manganese, magnesium and manganese. They have combined together with silica to form these components which are porous inside. So when you're high temperature, this is like gas expanding and cracking. But it took us a good 2-3 months to figure out what is happening. And there was no way we could have known if we did not know what the chemistry of the reaction is, right? If I just looked at the strength and whatever the minerality that came from, I would have said, wonderful material, why is this forming? So it's important to understand. And that's why I tell my students all the time. When you're studying concrete, you're doing the job of an engineer and the doctor at the same time. And I'll show you by today, tomorrow, we will do all investigative techniques that doctors put on human bodies now for concrete. I'll show you anything that a doctor has ever used. MRIs, I'll show you MRIs of concrete. CT scans, I'll show you CT scans of concrete. X-rays, everywhere. SEM microscopy images, everything that a doctor does to figure out what's happening in your system, we do to figure out what's happening in concrete, right? Because doctors, if they misdiagnose, one patient dies at a time. If you mistreat a bridge, many people die at the same time. That's the only difference. So there's always a joke, right? What's the difference between a doctor and a civil engineer? Doctor kills one at a time, a civil engineer kills many at a time. So you have to be very careful. Okay, so here is a hydration product as a function of degree of hydration. The previous slide was a function of time. And you see here, so what I started off was with the GEM software. I think it's a free software, you can download it for free. There are different versions of GEMS available free. For students, not for people in the industry, you don't have to bother about this, it'll bore you to death. But for students, it's a good idea to download that software. It's a little complicated. But for PhD students who are doing stuff with cements, I would strongly encourage you. It may not come in your thesis, but it will be a good learning process of how hydration happens. When you put in different materials, limestone, silica fume, fly ash, slag, all of those are different combinations, different reactivity, different chemical constants. It will give you a good feel for what is the equilibrium state of reaction products that you can expect to be formed. So, as a first step, when you get a certain fly ash with a certain constitution, you can run the software, thermodynamic software, to predict what are the ranges of products that will form, and if one or two products are not what you actually would want, that helps you to isolate the products. As a good forensic work to start off. So this is a GEMS model. You start with about 40% of water, and then you end up with about 20% of porosity, capillary porosity, this water. Start with 0 CSH, you end with about this much of CSH, this much of calcium hydroxide, this much of monosulfate and ethringite together, but towards the end it's only ethringite. C4A, C3A, C3S at 100% degree of hydration, C3S is totally consumed, At 100% C2S is totally consumed, C3A is consumed, C4AF is consumed, calcium sulfate, gypsum is consumed very early on here itself. See here it gives you a good picture of the entire process. Okay. Now we get into the story of a microstructure. All of you have seen pictures like this? Okay. So this is a very nice first order picture that I can show you a lot of different things what is happening. Okay. Now, it's a scanning electron microscope. How many of you have used an SEM? Did you use it or somebody else used and took pictures for you? There are two types of SEM users, okay? And this is a joke. I use it as a joke to my students. There are real SEM image takers and there are photographers. People who really look at and find what they want. I have my students who come, Professor, I got this wonderful picture. Oh, you're a very good photographer. What you get out of this? Nothing. Beautiful picture. Can I publish it? No. I tell them, make it big, frame it, send it to your parents, or hang it in your room. Wonderful picture. Do we find anything in it? No. So I can't publish it, but since you've gone through the pain of doing it, might as well use it for something, right? So you have photographers who will take a lot of wonderful pictures, and you look at some journals, and there are some papers that are published with plenty of good SEM pictures. They are photographers mostly. But sometimes we get impressed by these photographers, right? Maybe they get these wonderful pictures from. You're not looking at what have they found. And then there are the real SEM guys. The picture might be blurry, the pictures may not be the greatest, but they tell you a story. Okay. So this is a good SEM picture. This is not just a photograph, it's a good SEM picture. So if you have used an SEM, it's a scanning electron microscope, right? It's based on electrons. You're bombarding electrons onto a surface. All of you know that there are two ways in which you can do a scanning electron microscopy. You can do a secondary mode and a backscattered mode. In both modes, it's the electrons that are doing it. So electrons impinge on a surface and the electrons will bounce back. If the electrons impinge on a pore or a void, they will not come back because the void has no mass in it. It cannot bounce back. Therefore, it will go into a big black hole. Therefore, you will get the picture black. So whatever you see black, pitch black in this picture has to be void or pores because there is nothing for the electrons to be reflected on. Electrons will reflect more. So anything will reflect. If I put a ball down, if the surface is really hard, the ball will bounce much more. So if you have a hard surface, electrons will bounce much more, or all the electrons that went in will come back. Therefore, I will get a very bright image. Anything very, very bright in that is going to be hard. Yesterday somebody asked me, how do you identify different things in an SEM? This is the first way that you think of identifying. Anything that is bright is bouncing off of an extremely hard surface. If I take concrete, if it's not lightweight aggregate concrete, general concrete, what is likely to be the hardest thing in my concrete? Aggregates. Which means if I take an SEM image of a concrete, the brightest parts that I see are likely to be aggregates. If you do mortar, the brightest parts are likely to be sand. So you should know whether you have imaged a mortar or a concrete or a cement mix. But that you can easily know from the scale bar, which I have not put in this image. You will see the scale bar, and based on scale bar, you know the size. If it's less than 30-40 microns, it's typically a cement paste. If it's 1 mm, 300 microns, 400 microns, it's typically a sand particle. Right? So you will know that. Okay, so in this picture, actually, I said high aggregates are the brightest part, right? But you see something else much more brighter than aggregates there? Towards the right end of that picture. That's not an aggregate. What is that? What is the specific gravity of typical aggregates that we use? 2.6, 2.7. What's that cement? What is that bright white thing there? Unhydrated cement. So anytime you see the brightest thing, will typically be unhydrated cement. The brightest thing, unless you have a heavyweight aggregate that you put in, typically the brightest thing will be unhydrated cement. And when it hydrates, it starts to darken up. So here are aggregates, these are all sand particles. You can see those sand particles which are brighter. And then this area, bright, very dense reaction product. See that? This area, so this is a nice picture that shows you the contrast. Very dense reaction products here, very porous reaction products here. See that? In one picture you see everything. Dense reaction products, much more cement hydrated. Maybe there was more water available here. Water was not available that much here. Or there was way more water available to create pores. Either way, not enough cement grains. So you see here, porous. You see here this deposit on the sides, calcium hydroxide. Okay? Because you typically know that's calcium hydroxide because calcium hydroxide has a tendency to form on surfaces. Calcium hydroxide, being a precipitate, has a tendency to form on surfaces. Therefore, anything that's typically on surfaces, like here, you can do an EDX there at that point and find out other than calcium and hydrogen, what else do you have? That's calcium hydroxide. You see some bleed channels where water has gone through very large pores. You see some micro cracks happening from the aggregate paste interface. See some nice cracks here. This is a fairly old paste, so you see very well hydrated zones. Another particle of symmetry or porous region. Gives you a good idea. Another well hydrated region. Very likely, this could have been a microstructure where the sample was kept on a certain depth of water. And this part corresponds to the place where it had water. This part corresponds to the place where there was not enough water. Like, otherwise we don't know how it was done. Okay? So this is a standard picture. Now, if you use a transmission electron microscope, anybody used a TEM? TEM is the big brother of SEM. So SEM, typically, you can go to magnifications of roughly, how much? 5 and 10,000 is what you want in cement paste. You don't want more than 5 or 10. But typically SEMs will go to magnification of 100,000, 1 lakh. But if you want even more magnifications to 3 lakh, those kinds of magnifications to really look at what is happening, then you use transmission electron microscope. So scanning electron microscope, the electrons were scanning through. Transmission electron microscope, the electrons will have to be transmitted through the sample, which means your specimen has to be very, 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 very thin. Very difficult to make a thin sample. Very thin in a way that your cement paste sample should look like a thin film through which the electrons will pass through. Very difficult to make those samples. But if you make that, you will see how CSH needles are forming in the early stages. All of these are CSH needles. You will see a calcium hydroxide crystal being formed here. These are all needles of CSH that are starting to be formed. Okay, so here is another, so this was a backscattered picture, you can see that. This one was a backscattered electron microscope because you have a really flat surface, right? This is polished in such a way that it's all the same level. You can quantify. So if you want to quantify how much of hydration products, you want a backscattered electron microscopy because you want to have a level surface, so you get a 2D quantification of what you have. I will talk to you more about image analysis and quantification and 2D and 3D and what you should think about later on. Okay, this is a secondary mode, which is just a fracture surface. It is not polished, so you will see it ups and downs everywhere, right? And what are these plates, hexagonal plates? Calcium hydroxide. You will see a few needles here. See a few ettringite needles. And all the rest of the amorphous products are CSH. So amorphous, very loosely, not very ordered products of CSH. Plates of calcium hydroxide and some needles of. Yes. This one is, I don't know, this one is a magnification of 15 kV, 0.5, 500, 0.5 kV. This is a magnification of 500. This is a magnification of 1000. So very low magnification. That's all you need to find out calcium hydroxide and CSH. You don't need to go to to $500 and $6,000. Yeah, actually what happens is you need to apply sputter coating on top of this because you need a charge surface. Otherwise you have very high surface charge. So if you go very high, you will get very line blurry images because the charge will never be uniform on very heterogeneous surface. But if I take a piece of iron and polish, I can go to 100,000 and get clean, beautiful pictures. For cement paste, it's fine. Yes, you have to use whatever is the sample size. So basically, for concrete, if you want to look at the interface, then you should prepare a sample with part of the aggregate and part of the cement paste. You can't take a chunk of concrete and put it in the cement, right? So there is limitations on size and limitations on, because the idea is electrons are very, very small. So you have to have some comparative size compared to size of electrons. Okay, so hydration, same idea. Initial mix with lot of water, early age CSH form, later age lot of CSH, some calcium hydroxide, some unhydrated grains. Just to give you that picture. So CSH, we'll do another 5 minutes and stop. Yeah, I'll just finish this structural hydrated base and we'll stop. Okay. So calcium CSH is 50 to 60% of volume. Calcium silica ratio ranges from 1.5 to 2. It's a poorly crystalline network which you've seen. It resembles a natural mineral called tobermorite. Therefore, a lot of people used to call CSH as tobermorite. If you look at old books, it's always called tobermorite. If you look at old papers, they will say tobermorite. I would encourage you not to use that term anymore.